All right, let's get right into it. Today, we're doing a highly detailed, professional breakdown of the source material to uncover the absolute reality of high-bandwidth flash, or HBF. We're going to cut right through the industry hype and carefully examine the hard data. We'll rigorously break down its mechanical promises, its severe thermal limitations, and its true strategic purpose in next-generation AI infrastructure. If you're looking for a focused, expertly detailed analysis of what's actually happening under the hood, you are in the exact right place.
To keep things completely objective, here is our roadmap. We'll start with the physical limits of current AI memory, move into how HBF actually works, tackle GPU heat and degradation, look at the very real packaging risks, and finally wrap up with the hybrid data tiering strategy.
Section 1. The physical limits of AI memory. Before we evaluate anything new, we really have to look at the physical and financial brick wall that current high-bandwidth memory, or HBM, is slamming into.
You can see the core problem brilliantly illustrated right here, the dreaded AI memory wall. On one side of the chasm, you've got traditional SSDs. They're just way too slow with massive latency, literally starving the GPU of data. But on the other side, HBM. It offers incredible bandwidth, sure, but it hits severe capacity limits and, frankly, insane costs. And that massive gap is exactly what sparked the industry rumor mapped out on the right. The idea of a processor on NAND stack just outright replacing HBM. People have been whispering that standard NAND might step up to become a primary compute partner, pushing HBM to the sidelines.
But when you actually put these two technologies side by side, the architectural differences are night and day. HBM runs on volatile DRAM. That means it needs constant, power-hungry electrical refreshes just to keep its data alive. HFIF, on the other hand, uses non-volatile NAND. No constant refresh needed. That gives you massive capacity and a way lower total cost of ownership. But, and this is a big but, HFIF has a glaring primary weakness: wear limits and cycle degradation. Because of that, its architectural role is really built for throughput-oriented massive storage, not the split-second compute execution that HBM handles.
Moving on to Section 2, the emergence and mechanics of HBF. So, the obvious engineering question here is, if HBF uses inherently slower NAND, how on earth does it hit the massive read speeds that modern AI processors need? Here is the secret. HBF doesn't actually make the individual NAND cells any faster. It doesn't have some magic property altering physical single-cell speed limits. Instead, it relies on extreme parallelization to just bypass those limits altogether. Think of it like this. Instead of trying to build one hyper-fast sports car, they just deploy a fleet of 1,000 delivery trucks all at once. It maximizes concurrent channels, dies, and planes simultaneously. And all of this traffic is orchestrated by a specialized logic-based die, acting as the master conductor.
If you look at the bottom of this blueprint, you can see that slow data stream entering the logic-based die. From there, it directs thousands of concurrent channels flowing upward across a super-dense 6-plane NAND architecture. It's forcing extreme parallel execution. By opening all of those lanes at the exact same time, HBF can pull off massive read bandwidths. We're talking 1.6 or even 3.2 terabytes per second. It completely sidesteps the inherent slowness of an individual NAND cell, purely by reading from a ton of them concurrently.
Section 3. GPU heat and degradation. Now, bringing all that data right next to the processor creates a massive physical conflict. You are putting highly temperature-sensitive NAND right next to a giant thermal exhaust.
You are essentially parking NAND next to a 1,000+ watt furnace. And look, even with advanced ambient immersion cooling, you absolutely cannot stop microscopic thermal spikes from ravaging that high-density package. Why is that so bad? Well, look at the microscopic reality governed by the Arrhenius effect. Heat acts like a physical propellant. It assaults the NAND cell, breaking the energy barrier of the charge trap and causing it to violently bleed electrons. The rule of degradation here is absolute. The hotter it gets, and the more you use the cell, the faster it bleeds charge and dies.
Section 4. Packaging risks and design compromises. Because ambient cooling can't completely stop those microscopic thermal spikes, system architects are backed into a corner. We really need to understand the steep cost of this physical proximity.
Let's trace the catastrophic systemic risk introduced by the CoWoS packaging trap. Step 1. Your assembly has a 16-die HBF stack permanently packaged right next to a highly valuable $10,000 plus GPU. Step 2 is the trigger. Under all that massive heat, let's say just one single NAND die out of the 16 hits its thermal limit and fails. Step 3 is the brutal constraint. Unlike a standard enterprise server where you can just hot swap a dead drive, this die is physically irreplaceable. Which brings us to step 4, total package bricking. That one localized failure means your entire multi-thousand-dollar compute package is completely scrapped. Game over. To survive that intense GPU heat envelope and avoid bricking the whole system, engineers are forced into an incredible compromise. Standard TLC mode gives you amazing 100% capacity efficiency, but its complex 3 bits per cell operation makes it extremely vulnerable to heat. So, HBF has to shift into PSLC or pseudo-SLC mode. This simplifies operation down to just 1 bit per cell. That gives the module excellent thermal stability and massively boosts its write endurance to handle the electron leakage. But look at the top bullet under PSLC. It severely slashes capacity efficiency down to just 33%. HBF fundamentally has to throw away its greatest asset, massive capacity, just to survive living next to the GPU.
Section 5. Hybrid Data Tiering Strategy. Once you recognize these strict limitations, our whole perspective changes. HBF is clearly not a plug-and-play replacement for HBM. It's a highly specialized component that requires strict workload bifurcation.
Data absolutely must be strictly tiered. Check out the upper pathway here. Static, read-heavy model weights belong strictly on the HBF package. You write them once, read them constantly. It perfectly leverages that high bandwidth without triggering the thermal wear and tear that destroys NAND. But look down at the lower pathway for the KV cache. That data is highly volatile. It's constantly being written and deleted. Put that on HBF and it will destroy the NAND. So KV caches absolutely have to stay on robust HBM modules or get sent over a network bypass to dedicated context memory storage racks known as CMX. They don't compete. They just handle totally different profiles of data.
Looking at the industry's response impartially, we are seeing two completely divergent physics philosophies emerging. On one hand, we have direct integration, championed by SK hynix and SanDisk. They want to shrink the physical distance down to the absolute minimum by integrating NAND directly onto the GPU package, accepting those immense thermal risks and zero replaceability just to get maximum proximity. On the flip side, we have the network bypass approach favored by Samsung. Their philosophy is to expand fabric speed using PCIe 6.0 and CXL networks, keeping that heat-sensitive NAND safely disaggregated away from the GPU in fully replaceable storage nodes.
So as we move from lab testing toward real-world system deployments over the next few years, the entire future of AI infrastructure hinges on one massive, pivotal question. Will the cloud ecosystem actually accept the massive financial risk of irreplaceable packaged NAND just to shatter the memory wall? The engineering promises incredible leaps in capacity, but the physical reality carries unprecedented economic risk. It is a fascinating battle of speed versus physics. Thanks for joining me on this professional deep dive analysis. Hopefully this detailed breakdown of the data gives you a much clearer understanding of the high-stakes engineering that's literally shaping our technological future. What do you think the industry will choose?